5 kilometers. Alright, let's do another one. A wire with a resistance R is stretched to twice its original length. What is the resistance of the new wire? For example, if this is the original wire, you apply a stretching force and stretch it to twice its length. What happens when you stretch the wire? Its thickness will reduce, right? Okay. Well, let L be the length and A1 be the area of cross-section of the original wire. So the original wire has the length L and the area of cross-section A1. Then the volume of the wire. How do you find the volume of the wire? Volume will be length multiplied by the area of cross-section. So area, or the volume, not the area. The volume of the wire will be length multiplied by the area of cross-section, A1 times L. Now after stretching, its length is 2 times the original length. And its area of cross-section obviously is smaller now. Let that area of cross-section be A2. What is the new volume? The new volume will be 2L times A2. Is that right? Yes. So the volume of the wire now is V equal to A2 times 2L. Now are these two volumes different? By stretching the wire, have I changed the volume? No. The volumes are the same. That means this volume A1 times L equal to this volume that is 2A2 times L. So because the volumes are the same, I can now write A1 times L equal to 2A2 times L, and that gives us a relation between A1 and A2. A1 divided by A2 equal to 2. Now we can now use this to calculate the new resistance. What is the resistance of the wire when it is stretched? Well, we keep this value A1 over A2 equal to 2. Before stretching, its resistance is R, and let's write down a relation for that. What does R depends on? R equal to rho L over A1. Is that right? Yes. So original resistance before stretching, its resistance is R, that R equal to rho L over A1. That means I can now solve for L from there. That is L equal to R A1 divided by rho. Now after stretching its resistance, let's call it R prime. Can you write a similar relation for R prime? What happened? This length L becomes 2L, and this area of cross-section is now A2. So that resistance R prime equal to rho times 2L. This length, the length has become twice the length, and the area, the new area of cross-section is A2. So this is the new resistance R prime, and this is what we want to find. Well, all I need to do is I'm going to replace this L. You see, I colored it red. What is that L equal to? We have it here. L equal to R A1 over rho. So replace that L as R A1 over rho. And what you have now in here, that will be 2 times R. Look at this. Rho and rho will cancel. We don't need the value of rho. That will be 2R times A1 divided by A2. So R prime equal to 2R times A1 divided by A2. Okay. Well, we know A1 divided by A2. A1 divided by A2 equal to 2. Therefore, R prime, the resistance of the wire after stretching, is 2 times, well, 2R times A1 divided by 2 is 2. And that gives you 4R. So, when a resistor of length L is stretched to twice its length, its resistance now is 4 times the original resistance. Alright, I hope you understood the way I solved this problem. Look through it one more time. Another problem. A conductor of uniform radius 1.5 centimeter carries a current of 5 ampere. If the electric field in the wire is 150 volt per meter, what is the resistivity of the material? Well, so a conductor of uniform radius 1.5 centimeter carries a current of 5 ampere. The electric field in the wire is 150 volt per meter. What is the resistivity of the material? Now, what other things we have? Resistance R, the radius R of the wire is 1.5 times 10 to the negative 2 meter. What else do we know? If the radius of the wire is 1.5 times 10 to the negative 2 meter, what is the area of cross-section? Area of cross-section is pi r squared, and that will be pi times the square of the radius. That gives me 7.1 times 10 to the negative 4 meter squared. So we know the area of cross-section of the wire. We know the current in it, I equal to 5 ampere. We also know the electric field in the wire. Well, if you know the electric field in the wire, which is 150 volts per meter, what will that lead us to? Do you know that the old equation we have, E equal to dV over dr, or dV over dx. That means dV, the potential difference, is electric field times the length of the wire. The dx is the length of the wire, because potential difference is between the two ends, and the length of the wire, delta x, is between the two ends of the conductor. Well, E equal to 150 volt per meter. Let the length of the conductor delta x be equal to L. We don't know the length, so delta x, the length of the conductor, be equal to L. Then this is delta x equal to L. The electric field E in the conductor is, alright, one more time, what's the equation? E equal to delta V over delta x, which is V over L. So the electric field in that conductor is potential difference between its ends divided by the length L. Now, if V is the potential difference between the ends of the conductor, then that V equal to E times L. Is that right? If this V is the potential difference across the ends of the conductor, that V will be equal to E times L. And E is given to be 150 volts per meter, and L we don't know, so we leave it like this. So we got the value of V. Well, look at this. We know the current in the conductor. We now know the potential difference across its ends. What will that lead us to? You got the current, we got the potential difference. Therefore, what other information can we obtain using that? We can find the resistance of that conductor. Alright, so the voltage is 150 L volt. Alright, the current is 5 ampere. The potential difference is 150 L volt. Therefore, the resistance of the conductor is R equal to V over I. And what is the V, the potential difference we obtained? 150 L volt. The current is 5 ampere. Therefore, the resistance is 30 L ohm. You can see we don't know the length of that wire, so we keep that length. 150 L volts divided by 5 ampere is 30 L ohm is the resistance. What are we looking for? Well, we are looking for, I forgot what we're looking for, but we know that we are now in the territory where we use the resistance of the conductor to figure out whatever we are looking for. R equal to rho L over A. Now, we know the resistance, is that right? And we know the area of cross section. Well, and therefore, can you find the length of the conductor? Well, we don't need the length. We got R, we replace R by, what is our R? 30L. So 30L equal to rho L over A, and the length will cancel. We get therefore rho equal to 30A, and that will be 30 times area of cross section we know is 7.1 times 10 to the negative 4, and that is 0.021 ohm meter. So this is what we were after, rho. So look at the path we took. We used the electric field to calculate the resistance of the conductor in terms of L. And when that resistance is brought down here in this equation, the length got cancelled. And we could now solve for rho, the resistivity of that conductor. Okay, let's do another problem.